This section of physics studies the temperature and heat and their relation to work and energy. Thermodynamics describes macroscopic variables like pressure, entropy, and integral energy, which partially define radiation or a body of matter. According to thermodynamics, the actions of those variables depends on the general constrictions which are mutual for all materials beyond the unusual properties of specific things. The macroscopic explanation of processes and bodies can be referred to as thermodynamics in plain terms. Default to equilibrium as contract to non-equilibrium is what denotes the plain term thermodynamics. The competent term statistical thermodynamics denotes the explanation of processes and bodies in terms of the other microscopic constitution of matter or atomic using probable and numerical intellectual. One of the vital concepts in thermodynamics is thermodynamic equilibrium. The most distinctive quantity and well-defined system of thermodynamics is its temperature. The exact study of thermodynamics gets more tough if the processes and systems of curiosity are moved away from the thermodynamics equilibrium. Comparatively easy estimated calculations, still using the variables of equilibrium thermodynamics, are of much applied value. Many essential applied engineering circumstances, as in refrigerators or heat engines, can be estimated as structures containing of many subsystems at diverse pressures and temperatures. If a physical procedure happens very fast, the equilibrium thermodynamic variables like temperature will not be properly set to supply a helpful calculation. There are 4 laws in fundamental types of entities in thermodynamics. However, originally there were 3 laws which have now been classified into 4. The 0th law says that if there are 2 bodies which are in equilibrium with the third body, then they are also in equilibrium with one another. Hence, temperature is established as a fundamental and measurable property of matter. According to the 1st law, the total rise in the energy of a system is equivalent to the rise in thermal energy and the effort done on the system. This means that heat is a form of energy and is thus subject to the principle of conservation. The 2nd law states that heat energy cannot be transmitted from a body at a lower temperature to a body at a higher temperature without additional energy. Now you know why air conditioners are expensive to run. The 3rd law states that the entropy or waste energy of a crystal at absolute zero is 0. Entropy is at times referred to waste energy, which is the energy that is incapable of doing any work, and as there is no heat energy of any kind at absolute zero, there can be no waste energy. Entropy is also a degree of the disorder in a system, and despite the fact a perfect crystal is by description flawlessly ordered, any positive value of temperature signifies there is motion inside the crystal that leads to disorder. Because of this, there can be no physical system with entropy lower than that. Hence, entropy will always have a positive value. It is important that a physical system's internal atomic mechanism falls into one of the 2 categories for statistical thermodynamics and thermodynamics to apply on it. The atomic mechanism should be so fast that in a given time frame, the atomic states speedily bring system to its self-state of internal thermodynamic equilibrium. The atomic mechanism is so slow that in the given time frame, the system is left unchanged. The fast atomic mechanism is because of the internal energy of the system. They are mediators for the macroscopic alterations which are concerned for statistical thermodynamics and thermodynamics, as they bring the system close to thermodynamic equilibrium in no time. Statistical mechanics and thermodynamics are not applicable if intermediate rates are present, as this rate of atomic processes doesn't bring the system close enough to thermodynamic equilibrium within the given time of the macroscopic process of interest. The separation of time gauges of atomic processes is a theme which repeats all through the subject. Like the traditional thermodynamics is categorized by its study of resources which have or characteristic equations or equations of state. They prompt equilibrium associations among temperature and inner energy and macroscopic mechanical variables. They show the organized individualities of the material of the system. A conventional material can normally be explained by a function which makes pressure reliant on temperature and volume. The pressure which is built is much faster than any enforced modification of temperature or volume. The specifics of thermodynamics could be elucidated by describing objects as assemblies of atomic objects which follow Hamiltonian dynamics. The atomic or microscopic objects occur in species, and the objects of all species being the same. This cause of resemblance and statistical methods could be used to account for the macroscopic characteristics of thermodynamic system as per the characteristics of microscopic species. This description is known as statistical thermodynamics and is at times denoted by the term statistical mechanics, although this term could have a broader meaning, speaking of microscopic objects like